Hello, everyone. It's 2:30. We're going to get started here. So this is session for data flow, and our first speaker is going to talk to us about DataKnots. Clark and Carolo is known for co-founding YAML, if you're interested. Okay? Let's welcome the speaker.
Hello, everyone. So my name is Clark Evans. I'm a co-founder of Prometheus Research. We've been doing medical system development for medical researchers and institutions in here, sorry. So we've been doing research systems for medical research and research registries for quite some time. And Krill is my colleague and good friend who I've known for quite some time. He's the co-author on this work. So today I'd like to talk about DataKnots, which is an extensible query language. And it's a pure Julia implementation. It is MIT licensed, and it's up on GitHub. And in order to go in a little bit further, what I'd like to do is start with the business problem that we work with. And the main issue that we deal with often in medical research projects is that that these medical research projects have a very clean but multifaceted workflow with many participants. So a project would go through an inception, and this is usually by a principal investigator, which would move on to a feasibility study, which would say, do we have enough data in our hospital system or other research areas in order to even conduct this study? Then it would move on to a missing chart review, and then a loop where data set is generated from multiple institutional data sources, integrated, statistical analysis is done, and then results are calculated, and this whole circle returns. Now, what's important about this particular diagram, and I think this is the state of the art, the way that best research projects are done at Columbia and other places, is that they involve multiple people. And these multiple people are using different languages. They're using different ways of thinking about the problem and thinking about the data that they have. A principal investigator might be saying things like, which antihypertensive medication is effective in improving blood pressure, or clinical research. And well, an informatician is going out to an electronic health record system and making queries, select patient from observation, where, and a bunch of joint conditions and everything else. And this is much lower level. And then you have a statistician who would be using R or some other tool that is pulling together all the CSV files produced by the informatician and then computing results, which goes back to your principal investigator, and this loop continues, right? And the idea that all of these people are using different languages seems like an inefficiency to me. And this problem is not just limited to medical research. It happens everywhere in most institutions. And but I can give you a really clear example and there's other people involved in this, not just a principal investigator, informatician, or statistician, but usually there's so much data that someone fetching from an EHR wants to do that someone wants to build some visual screens on top, so that clinicians could access the screens themselves. And these screens I'm going to tab over might look something like this. So this comes from Odyssey, which is an observational research group. It's an open source project, MIT licensed. And in their common data model, which is a SQL data model, they have numerous tables that are interrelated that hold key information from the electronic health record system that someone might want to query. As you can see, this is a fairly simple screen for defining what a cohort is. Once you define, a cohort would be a set of people of interest. And in this particular case, someone might be interested in someone who has a heart attack, and then basically that happened when someone had an emergency visit, and there's other criteria as you go down below. This kind of screen is written by a user interface developer. And if you ask them to query the developer themselves, they're not going to go to their screen. They're going to go directly to the database and write SQL or use their favorite tool like Link or whatever other tool. They're not going to go back to the same user interface that they themselves wrote, which is a bit of a challenge. In any case, what these screens would generate, in the case of Odyssey, is in fact a JSON file, which is a sort of a mini domain-specific language which encapsulates the information on the screen. This then goes into a Java program which produces some SQL. And the SQL might be tailored to a particular database system. So this is an example of what I mean by a domain-specific language. It happens to have numerous components, and it's there to help bridge this gap between multiple participants. So let me get back to our story. What we would like to do, and the main goal of this project, coming from a high-level business perspective downwards, is that we would like to make it easier to construct these domain-specific query languages so that people can build visual screens on top, people can, a principal investigator or clinician or other researcher could look at the query themselves and say, yeah, that's what I'm after. And for example, the informatician might be able to work at a higher level, and the statistician could be rolled in to where they can participate in the queries themselves to have this whole communication cycle go better and more smoothly together as a single team. This is an emerging factor, and they call it team science, and there's a lot of papers on it written the last few years, and there's even a conference on team science. So I think there's a huge opportunity for Julia in team science. It is an amazing statistical language, a general purpose programming language, and as I hope I will show you today, a wonderful language for making high-level domain-specific query languages that domain experts could use that are not necessarily programmers. So let's consider just a simple question. Which antihypertensive medication are effective in improving blood pressure? We could operationalize this as within 6 months of an antihypertension or a hypertension diagnosis, when antihypertensive medication was added or intensified, was there a blood pressure decrease of 5 millimeters or more within 5 days of medication adjustment? Okay, it's a mouthful. But the thing is, when you're an informatician looking at this, the highlighted words pop out. These are your nouns. These are the operational terms to which your user community is thinking about their data. These are the words that they use and the way that they're thinking. So you would sit down with this group in a setting and say, what do you mean by these words? And each one of these components would become elements of a high-level domain-specific query language that you're targeting for this sort of question. Once you have these things defined and you've gone through review, tested them, made them into something that you can verify that, yes, that actually means what it means, and it represents what the user community thinks it means, then you can take that previous inquiry and make it into an actual database query that would go out to the various record sources, data sources it needs, and do the various computations necessary. So let me walk through this query just really briefly. So this starts off with patients and it's saying, for each patient, keep it because I might need the patient later. But for this patient, go through their antihypertensive medications, compute the active ingredients for those medications, then figure out when they've adjusted, when they've gone up or down. Then for each one of those, I only want to see medication adjustments that have been added or intensified, and that the previous 6 months includes a situation where the patient has a hypertension diagnosis. Then, what I'd like you to do for those medication adjustments, I'd like you to compute a variable. This is something that you're going to collect with the current data set, and we're going to call it isEffective. And this means in the subsequent 5 days that this particular time period includes a patient blood pressure decrease of 5 millimeters of mercury. Once you've made that computation, group them by active ingredient. I'm not just interested in the medication adjustments. If you look back to my original inquiry, I was actually interested in the active ingredients. And then, from those active ingredients, count the medication adjustments, filtering by if they're effective or not effective. Now, this is a mouthful. I don't expect everyone here to get it because there's a lot of domain-specific words. But this is something that you could put in front of a high-level analyst. It's also, really interestingly enough, each one of these query components is a Julia, has a Julia binding to it. So you could include, for example, right in the middle of this pipeline, a statistical operation and integrate that in your data set, which would be awfully cool. So in order to explain how this query works, I would like to discuss a little bit about the high-level algebra that DataKnots has. So DataKnots starts in 4 levels, and the lowest level of DataKnots is just a directed graph. And you can think of it as an infinite tree. And you can take any relational database and project it onto an infinite tree. You can start with a starting point, and as you navigate through relational links, you can grow the table. And of course, as those tables might refer to other tables, those create further links in the subtree. And those might actually refer all the way back up to the top, which means that you're going to continue down a really large infinite tree. So that's the main underlying data model of DataKnots. And on top of that is a hidden implementation layer, which are basically data pipelines. And that implementation layer is where someone writing query components in Julia would use. But right above that level are queries and query combinators. And that's what I want to talk about here. So from a user's perspective, you might start off with an EHR, electronic health record system, of just 2 tables, right? This is a simple relational database, let's say, or it's 2 separate tables that you load into 2 data frames and relate them, or join them. And so we have patient, and a patient has multiple conditions. Now, that's not how we view the data. We view the data as a hierarchy. So this relational model, right, is sort of pivoted. We're going to start with the database as a whole, which is the circle. The database as a whole in this particular, it's a very simplified model, by the way. It doesn't show all the graphs. It doesn't show all the recursions. I just made it simple for this particular display. But the database as a whole has a number of patients. And from those patients, they have a number of conditions. And the patients have identifier and birth date. And the conditions have a category, onset, and an optional abatement. And that reflects the table here. So you can map queries on top of this structure, and this structure is something that a high-level clinician or any one of your domain users might actually be able to use quite easily, as opposed to these tables directly using SQL. And this hierarchy creates and motivates a kind of a query language, which is path-based. And the way that the paths work, or the way the queries work, is reminiscent of XPath. Indeed, when we started to work on query languages like this, I had previously done an XPath implementation. And so it was foremost in my mind, how can I get an XPath that works on relational databases? And an earlier version of this works slowly from an XPath-like syntax onto SQL. The current version, which is rewritten in Julia, and boy, did it get faster, is basically an in-memory data structure, and we will later on add pushdowns to relational databases so that we can tightly integrate multiple data sources. But the current implementation of DataKnots is an in-memory data structure. But as you can see, these particular queries are motivated by this structure. The first query will return you a list of patients. The second query will return you the count of all the patients in your database. The third query is going to, for every single patient, list all of the conditions in the database. And the third query is going to, for each patient, count the number of conditions they have. And then finally, the last query is going to give you the average of the condition counts by patient. So this is a fairly unambiguous definition, and each one of these pieces work together in order to make a whole. So now this high-level part of the system, which is visible, which users can build user interface screens on and send down as JSON, or you could use directly in a macro query language, or you can directly use with Julia without macros. This language is an algebra, and it's a multi-sorted algebra. And the algebra's elements, which we call queries, are relationships between types of data. For example, between the database as a whole and a patient, or between a patient and its conditions. Okay, those are the queries. And the operations are combinators. They take queries as arguments. So for example, count is a combinator, and it takes the query patient, let's say, as its argument, and it converts and makes a query. So basically this algebra is closed. It's a closed system. You're not dropping down into Julia once you're in the system, which is useful for lots of other reasons, in terms of being able to have a clean subset language that you're limiting your users to. Now, how do you convert the hierarchical model, or how do you convert the tabular model to the hierarchical model? And this is more of an implementation detail, but you can think of it as a functional database underneath the sheets. And each of your data elements, such as a database or patient or integer, these are your data types. And your query, patient, would go from the database to the patient, or from the patient to an integer would be the identifier query. From patient to condition is the condition query. In this diagram, queries are not capitalized, where the data types are capitalized. So once you do that, you can see that queries get a signature. That is, we know where they come from and where they go to, and they are viewed as functions. So the queries, the patient goes from the database to patient star, and the birth date goes from patient to a date time, let's say. Now, these are your primitive elements in your algebra. You know, like 1, 2, 3, if you think of them as numbers. And your operators then are things like count, which we'll talk about in a moment. Now, the thing is unlike elementary algebra, this algebra is sorted. The actual queries have a signature, and the signature is the type of the query. Okay, so how does a count combinator work? Well, the count combinator takes any function f, going, let's say, from a query A to B star, and it converts it into count of that query, which would go from an A to an integer. So since we know that patient goes from database to the number of patients, we know that count of patient goes from a database to an integer. Since we know that condition is a query from patient to condition star, we know that count of condition is also a query, and it goes from patient to integer star. The composition combinator is fairly straightforward, right? A dot B. And this is your hierarchical navigation as you go down the tree. You're going from patient to condition to let's say the condition's onset. You could put a period between them if you wish. And the composition takes two queries with a signature, and you can compose them if, of course, the codomain of the first is related to the domain of the second. And there's more specific details about how all this works, but you don't have to have the types. The monadic aspects of these queries is that the cardinality, being more than one patient or just a single patient, are handled as part of the query infrastructure, if that makes sense. Anyway, let's see how this works in practice. Let's go back and look at a high-level question. Suppose that an informatician would like to conduct a feasibility assessment. How many patients 18 or older have an active diagnosis of essential hypertension? Well, you could define all your components. Essential hypertension with a definition. Age, you could define it. And the component, you can define it, or has active diagnosis. You can define that as the existence of a condition filtered by a category that matches where the abatement is null. Now, this is the Julia macro syntax on the right. The macro feature is really quite helpful. And with these components defined, you could define then a high-level query language and use it in order to answer this specific question, which would be, well, the patient where you're filtering where the age is greater than 18 and it has an active diagnosis of essential hypertension. So this is the basic high-level view as to how you could make things much cleaner and make them work for really domain-specific users and high-level users that are not necessarily working, with the nuts and the bolts. And just to review the architecture again, the layers are at the very bottom. You have a representation of the data as an infinite tree. We have pipelines, which we haven't talked about. Those are a very important implementation detail. And then we have queries and combinators. Now, what I just previously described about queries isn't completely true. Most of that algebra that I just described is actually true of pipelines. Queries are actually a little bit higher level of abstraction, and I'm not going to go into that today. But the whole idea is that you could build your pipelines in Julia, and you can export them into this algebra of queries and combinators that build them. Now, you're not limited to our macro syntax. You could just say, if you're attached this to, let's say, a Postgres database, you could say, patient, capital P, is get patient, where patient is the table name, or not the table name, but in our methodology, it's a link relationship between the database as a whole and that table. Sorry about that. And then condition would be get condition. And then you could do things like count a patient and patient, patient and then compose it with condition, or patient compose and count condition. So this is the Julia syntax equivalent. There's no reason to use the macro syntax. In fact, there's a lot of reasons why having native Julia is extremely helpful. The other thing that we have, which is automatic lifting of functions, if you take any string, you could lift it into a query. So hello world would become a constant query that produces hello world. And title case of lifting of hello world is going to call the Julia title case function as an array against a query that produces hello world, which should give you capital hello world. And then lift of 1 to 3 is going to give you a plural value of numbers 1 to 3. And then you could, for example, use other functions, such as if you import the statistics package mean, you could say mean of what is the patient count of condition. So anyway, these are the most important part from our perspective is that not just that we have a high-level query algebra that we can build and define for our user community, but we can extend it. And the query combinators overall and the DataKnots implementation has a well-defined API for constructing query primitives and for constructing combinators. And you express these in terms of operations on pipelines. And we can talk about that at another talk. Anyway, I would like to point everyone to DataKnots on GitHub. And I have a few things I'd like to point out before I take questions. The first, one of the fun parts is that I showed you this query from Atlas, yes, and I implemented this. Here is the DataKnots query that does what that screen does. It returns the same results when run against Postgres, against their database. So this is basically this is a real example, not just a made-up demo one. And what this does is it takes each person, it keeps them, and it says go to that person's conditions, keep the index date, or keep the start date. In the Odyssey terminology, the index date is the core date that they're tracking for that event in order to make the cohort. And then basically look at the continuous observations that are related and filter them such that they include the index date, assert that it's a singular value, 0 to 1, and then go ahead and find a correlated acute visit, go up to that same person, look at their visits, make sure that the concept is the right kind of emergency visit, and then make sure that that visit includes the index date, and that the time period also happens during the continuous observation previously mentioned. Then filter that this particular condition is a SNOMED concept with these two codes, which are heart attack, and also that there exists an acute visit. And then after you do that, you can compute a date interval of the index date plus the minimum of the index date plus 7 days, or the continuous observation end date, and then collapse the intervals into 180-day groups. So this is the succinct logic that represents what this Odyssey screen and what a large SQL query entails. So let me go back to just showing you the DataKnots. We're on the web or up on GitHub, and we have several parts of documentation. The first one, the main one, starts off with queries for data analysts, and this particular documentation I started to write a few months ago after we added our query syntax. So it has basically how to count and filter, how to do records, how to do aggregates, how to page, and how to group. And this is using the query syntax. There's also a small tutorial saying, if you were going to start with some data, let's say some City of Chicago data, how could you load it as a CSV file? And then this is a query, by the way, that would return those employees having greater than average salary from data from the City of Chicago. And we trimmed the data set very significantly because there's the mini data set we're using. But there's the query, and this particular tutorial walks through an incremental development of that query. The other documentation available, this is an in-progress work called Thinking in Queries, which talks about how to think lower level and how to make queries and combinators using pipelines. So it talks about composition, identity, blocks, and cardinalities, and low-level details of how to build things. And how pipeline signatures, remember when we talk about query signatures, they're actually pipeline signatures. And then there is an earlier document I wrote, which is the which is more of a tutorial, but it's focused on the embedded query interface. So it shows how to build queries using Julia without the macro language, and talks about incremental construction, which is actually really cool. You can slowly build your queries and execute them. And it talks about summarizing data and grouping and all those sorts of things. And then there are a bunch of documents that describe the low-level architecture if you want to help join us. And we would love help. We would love people to find the project helpful. And if you wish to join us, please. It's an open project. We've documented how the column store works, how the pipeline algebra works, how the shapes and signatures of the queries or the pipelines work, and the actual query algebra itself and the operations on the query algebra. And with that being said, there is the project, and I really appreciate your time. I would love to have questions. We have 5 minutes, I think?
Yeah, we have 5 minutes. So if you have questions, can you please come up here to ask, or ask on your seat, but the speaker will have to repeat the question, okay?
Hi, really nice stuff.
Thank you.
My question is your column store specialized on the types of all of the columns? And if so, do you have problems with compile times? And if not, how do you get good performance?
The answer is it is specialized. I'm quite sure. That's a question that Kirill could answer in particular, but I'm pretty sure it's specialized. And I'm pretty sure that our query compilation times take time. The good thing is they're fast once they compile, which is great. And for a lot of the medical research queries we have, that's not a big deal. Also, you can parameterize the queries. And I would imagine that once you have a parameterized query, let's say you're loading up in the Google Cloud, and you start startup, you could construct your queries, parameterize them, and then at least you're only taking the hit once.
Okay, thanks.
So can you say something about how difficult is it to write these custom adapters? You mentioned talking to data sources on the web.
Yeah, that's great. That's a lovely question. Right now, we only have a CSV import adapter. Previously, we have an XML and a JSON adapter that we wrote. The code is there from previous work, but we'll have to port it forward. But it requires a merge operation, which we don't have yet. And it's mind-bending. In fact, we don't have sort implemented right now. And the reason why is because Kirill would like to make sure that I completely understand the pipeline algebra. So sort is our outstanding task to where once I can do that, then we know we're done. So, did I answer your question? It takes effort.
Okay.
But I've implemented a few, and they're not.
But they
I
can
don't
be.
have time.
But they can be quite generic depending on basically the serialization used. It's not necessarily the type of the format of the data.
Yes.
By which I mean which fields are in. That doesn't necessarily mean require updates to this.
No,
right? If you can parse a JSON format.
Those should be totally orthogonal. In fact, our Postgres adapter is totally separate, and it introduces a new type of table which is deferred, and I don't know the magic there. But the nice thing is that you could do federated queries with CSV in one, and then XML, and then maybe a couple of databases, and then query them together in a federated way. And pulling back, we eventually want to push down the SQL. That if you have a query tree this big and this part can be pushed down into SQL, we would, and then bring back the results and then integrate the rest. So I hope I answered the question.
That sounds great. I'll give it a look. Thanks.
I wish we had more funding so we could go faster.
So a very quick question. So the composition combinator is a join that drops the join column?
I wouldn't think of it as something that joins. It's basically a composing queries.
So if you have in your example, you had patient and condition.
Yes.
Patient dot condition, right? So you have patient can have many conditions, and a condition can be had by multiple.
If you convert that to SQL, you'll get a join.
Okay. All right.
Yeah.
Thanks.
There's a separate join operator which is used to do ad hoc links that are not are primitive. So I have to go. Thank you very much. I appreciate it.